Привіт. No. Я розповім про квантові комп'ютери та про постквантова криптографія. Але я не говорю українською. I'll speak in English, if you don't mind. That's the only words I know. So hello, I'm very happy to be here, very happy to have been part of this event and to be on the main stage. So thank you to the DOU organizers for making this trip happen. I come from Switzerland, so they also helped me with all the logistics, all the trains. So thank you, Vlada, and all the team for this. So, yeah. Quantum computers, how many of you have already used a quantum computer? Yeah, it looks close to zero. One, okay, not completely zero, but. So very quickly about me, I'm not a physicist. My background is in cryptography and security. I've been doing cryptography for 20 years, and 2 days ago, someone told me, JP, how do you mean crypto for 20 years? Bitcoin only appeared in 2011. I was like, man, there was cryptography before blockchain. You know, crypto doesn't mean Bitcoin and all, so in case you don't know about that, crypto is not only Bitcoin and all that stuff. So anyway, yeah, I've been doing a ton of crypto. I've been doing ciphers, which run in almost every computer and mobile phone. And today, I'm co-founder and chief security officer of a company called Taurus. I'm not here to do a commercial pitch, but in short, we do the wallet, the technology that banks use to protect their crypto and digital assets. So tokenized securities, Bitcoin, and all that good stuff. I've written a few books, and my last book is not technical. It's fiction, it's a novella. It's called Crypto, and it should be published in a few weeks, 2 weeks tops. Okay, let's start. So you may have heard about quantum computers on the internet, where people keep telling you that they're coming in 5 to 10 years, or in 3 years. It depends on the day and the weather that day. And we often hear about how quantum computers would break security of many systems, or would make a lot of people rich, VCs, investors, and it would enable quantum AI. Nobody has any idea what that means, but that sounds pretty cool if you put buzzwords together. However, the reality is that quantum computers were created for a more noble purpose, namely understanding how the universe works, how the laws of physics work, and specifically how quantum mechanics works. So it's an article from Dick Feynman in 1981 called Simulating Physics with Computers. And if you read the second line here, it says, can a quantum system be probabilistically simulated by a classical computer? And then I highlight the answer is no. Why? Because quantum physics is not about big stuff, it's about very small stuff, about subatomic particles, photons, electrons, quarks, and all that good stuff. And I will explain why you cannot simulate it just by programming a computer in JavaScript, C, Rust, or your favorite language. So he came up with the idea of a computer that is built of the particles it's trying to simulate, of particles that behave according to the laws of quantum physics, which are extremely different from the laws of how a planet turns, how gravity works. The equations are completely different. So it's not a Turing machine, it's not a classical Boolean circuit, it's not a JavaScript program, it's not even a program, as you will see. So maybe you've heard about quantum bits, or qubits. So in a computer, you have memory, you have the storage, and you have the program, typically. In the storage, you have data, which is encoded in bits, bytes. So the bytes are made of bits, and a bit is 1 or 0, or 2 states that we call 1 and 0 because it's just simpler. However, in your computer memory, when you store a file, well, the first bit might be 1, the second bit might be 0, and they do not change until you change the file. So 1 bit is 1 or it's 0. In the quantum world, it's a bit different. So one way to put it is to say, oh, the quantum bit is 0 and 1 at the same time between speech marks. So this, at the same time, is a simplification of a state called superposition, whereby a quantum bit is characterized by two probabilities, two numbers, alpha and beta. They're not the normal probabilities like we know. So it's not a 50% chance. So normal probability is a number between 0 and 1. 0 means never, and 1 means always. So it's a number between 0 and 1. However, in the quantum world, the probabilities are not just this type of number. They can be negative, and they can be complex numbers. So complex means using the imaginary unit, the number I, where I squared is -1. So these two numbers, what they mean is that when you observe the quantum bit, you say, hey, quantum bit, what is your value, 0 or 1? Then with probability alpha square, it will be 0, and probability beta square, it will be 1. So don't need to worry about the Greek letters. You can replace the Greek letters with any letters you want. But the point is that the quantum bit has no value before you observe it. It's not that the value is hidden and that you just happen not to know it. The value is not defined until you observe it in some way. So that's the very weird, crazy, and counterintuitive building block of a quantum computer. So a quantum computer is, in fact, a quantum circuit. You start from a state on the left hand. The left hand, you have quantum state, a list of quantum bits. 0, 1, 2, 3, 4, 5, and so on. So you can generalize what I said about a quantum bit to a quantum byte. A quantum byte can have 2 to the 256 values, and each value has a probability to appear if you observe it. The probability doesn't have to be evenly distributed. It doesn't have to be 1 divided by 256. It can be completely different. So you can characterize this state by all the probability of each possible value. So now if you have 2 bits, 2 quantum bits, how many possible values do you have? 0, 0, 0, 1, 1, 0, and 1, 1. So you have 4 values. If you have 10 bits, 10 quantum bits, how many values? 2 to the power 10, 1024. And if you have, I don't know, 100 quantum bits, you have 2 to the power 100 possible values. That is more than the number of atoms on this planet. So that's a lot. So you cannot have a vector in your memory with 2 to the 100 possible values. But if you wanted to simulate a quantum circuit, you would just have to take all these probabilities and multiply them by matrices like you learn in high school when you do vector time matrix operations. Okay, I don't want to bore you with math, but the upshot of this is that it's pretty easy to simulate if you have very few qubits, but if you have more qubits, it's physically impossible. So we cannot simulate it with a MacBook or with a Raspberry Pi or whatever. So why I'm here talking about this nonsense? Because there is something called quantum speedup. So quantum speedup is when you can do certain things, when you can solve certain problems much faster with a quantum computer or quantum algorithm than a classical one. So faster, that's the most important point, maybe if you want to remember one thing from this talk. It's not faster in the sense that we do the same thing, the same operations, much faster in terms of velocity. In fact, we're doing completely different stuff, completely different operations. It's not about porting your classical algorithm to the quantum hardware. It's about doing something that you could not ever do on a classical system. So those problems are computational problems that I will mention later. There are very few problems that benefit from this speedup. There's a class of speedup that we call superpolynomial, and in particular, the exponential speedup is when you can do something exponentially faster than the classical computer. So let's say you have a problem where it would take you, I don't know, exponential time to try all the possible keys for RSA, but maybe you have a quantum algorithm that is solving the problem not by trying all the values, but by doing something very weird, very differently. So it will not do the same operations faster. It will do completely different operations and much fewer. So there's a list of problems on this website, and I'll let you check it out. Another big misunderstanding when you talk of quantum computers is quantum parallelism. Because what is tempting when I told you, oh, it's all the values at the same time. OK, it's 0 and 1 at the same time, so the quantum computer, it's computing on all the values at the same time. Well, it's not really, it doesn't really work that way. It's not correct to interpret it in that way, because after the computation, you don't obtain the result of all the values. You can only observe one value, and this result is assembled thanks to the principle of interference, of quantum interference, something I don't have time to explain, but you cannot, let's say, crack passwords by trying all the passwords at the same time and then telling the quantum computer, hey, please tell me the password that works. No, it does not work that way, alas. It's more complicated. So the second thing I want you guys to remember is quantum parallelism. It doesn't mean trying all the solutions at the same time, because that's what you read in the news. That's what people repeat, but it's completely wrong. And in particular, so I mentioned the problem of cracking passwords that cannot be solved by quantum computers. And you may have heard of NP-complete problems. So it's the complexity theoretical term for certain type of constraint-solving problems, like SAT solving, traveling salesman, knapsack problems, where it's about constraint satisfaction, like finding the optimal scheduling in your agenda, finding the optimal placement of different puzzle pieces, that kind of stuff. NP-complete problems are really hard to solve, but very easy to verify. So I don't know if you guys are into video games. So in video game, there is a discipline which is like speedrun, where you try to finish the game as fast as possible. It's very tricky, very difficult, but when someone does a speedrun, it's easy to verify that their speedrun is correct, because you can just watch the video, see that they're not really cheating, and you can verify it efficiently. So it's the same idea with this kind of problem. It's hard to find a solution, but easy to verify. So there's this nice diagram that explains that the stuff on the right-hand BCP is the category of problems which quantum computers can solve efficiently. Efficiently, for theoreticians, it means non-exponential time. It means polynomial time using random numbers. And what is NP? So NP is not exponential. It means non-deterministic polynomial. It means stuff you can verify efficiently. So again, you cannot solve all hard problems with a quantum computer. So I will stop the theory here. There is this excellent book by Scott Aronson if you want to learn more about this topic. It also talks about system machine learning, time travel, cosmology, consciousness, life, and all that good stuff. OK, so the reason why the organizers got me here today is to talk about dinosaurs, if dinosaurs are public key cryptography. So I just did that using AI, obviously, like everybody does. So quantum computers could completely destroy all the public key cryptography you have in your computers right now. If you do SSH, IPsec, WhatsApp, TLS, you name it, all the stuff is completely destroyed by this asteroid called quantum computers. The question is, will cryptography disappear like the dinosaurs? Let's see. So the reason why dinosaurs, cryptographic dinosaurs, would disappear is that those two problems are really hard for us humans and for classical computers. However, they're really easy for quantum computers. And the first one is straightforward. It's about multiplication and the inverse of multiplication. So n equals p times q. Let's say 35 equals 7 times 5. Oh, it's easy to multiply 7 times 5. But how to factor go from 35 to 7 times 5? Oh, it is easy. But if the numbers are huge, it's really hard. If the number n is hundreds of digits, of decimal digits, then we don't have any efficient algorithm to crack it. That is why RSA is secure. And the second one, there's one extra letter. You have a number y equal to x to the power d modulo p. You know y, you know x, you know p, but you do not know d. Your problem is given those three letters, Y, X, P, find D. You're like, OK, that must be straightforward, because I have three letters, I just need to find one. No, in fact, it's really hard, and it's the reason why your TLS, your WhatsApp, your SSH, your IPsec is secure. If you could solve this problem, all that stuff would be completely destroyed. But yeah, boom, with a quantum computer, it's straightforward. You go from exponential to polynomial time. So how bad it is for crypto in practice? So I told you that all public key crypto would be broken. But public key crypto, it falls in three main categories. The first one is signature. Signature is the most resilient. Why? Because signature is not about secrecy. It's not about confidentiality. It's about authenticity, about proving that you endorse something, that you approve of something using a signature. So if you use, let's say, elliptic curve, DSA signatures, or anything that is breakable by a quantum computer today, and you just wait, you don't care about quantum computers, and one day everybody tells you that, oh, there's a quantum computer coming next week. You're like, oh, well, OK. I will issue new signatures using post-quantum, quantum-resilient signatures. So you can wait. However, when you deal with secrecy, do I have? No. So the last 2 points, key agreement and encryption, is when you deal with secrecy. So people sometimes talk of the attacks called harvest now, decrypt later. What you could imagine doing if you have a friend that has encrypted their messages and they encrypt them. So you collect all their encrypted messages now. You cannot make sense of them. But 20 years, 50 years from now, when you have a quantum computer in your pocket, you might be able to decrypt those messages. So that is why it's more important to find a solution to the quantum computer risk when secrecy is involved. So key agreement is when two parties negotiate a secret, like in SSH, like in TLS, and encryption is when you directly encrypt a file with public key crypto. Now, the good news or the bad news, depending on which side you are, is that we are extremely far from having a quantum computer that can break all the stuff. Well, that's my opinion, at least. Because you would need a quantum computer with millions of quantum bits. Why millions when the size of your key is hundreds or thousands of bits? Because a quantum computer is a very fragile beast. It works with very small stuff, electrons, photons, which are very sensitive to temperature, to vibrations, to acoustic noise, to electromagnetic noise. So there's a lot of errors in your system. So you need error correction codes, quantum error correction, and you need more qubits for that. So as of today, the leading companies are arguably Google and International Business Machines, IBM. There's this nice diagram, so that's a lot of colors here. You have two main dimensions to compare quantum computers. The first one is the size. How many qubits do you have in your computer? But it's not enough to measure the number of qubits. You have to know how reliable they are. How long are they stable, and what is the error rate? Because it's good to have thousands of qubits, but if they're unusable because they fail all the time, it's completely useless. So there is a very nice web page that is doing a very solid job in trying to explain where we are now in terms of technological progress and what could we do if we progress in either direction. And as you will see, so the part RSA is broken, crypto is broken, is quite far compared to other applications. So just to give you an order of magnitude, now we have between hundreds and thousands of qubits, but we would need millions, if not hundreds of millions of qubits to do something scary for crypto. OK. And you got to be very careful, because when you read the news, some people are very good at writing press releases, trying to exaggerate what's really going on. I was really sad when I saw that Google wrote in their press release that their quantum computer kind of confirmed the theory of the multiverse, the many-world interpretation. And of course, when journalists and a lot of people see multiverse, they just stop thinking. They just think of Rick and Morty and all that multiverse stuff, Spider-Man. And you had news saying, yeah, Google prove that we live in a multiverse, oh my God. And it can do in 5 minutes what other computers would take 10 septillion years. I have no idea what a septillion is, but that sounds a bit fishy. And Microsoft, they say that they discovered a new state of matter. Whereas if you know physics, you know that it's complete BS. So just be careful when you read the news about that. The last thing is quantum supremacy. What is quantum supremacy? Is it when everything is quantum? Well, everything is already quantum. I mean, my body is quantum, this Steve is quantum, light is quantum, obviously. That's the point. Quantum supremacy is when we have reached a stage of technology where we have quantum computers that can do certain things that we cannot do with our classical computers. It doesn't have to be useful. It just has to be. So Google did something that is very quantum by definition, sampling quantum circuit that you can describe as a computational problem. And they were like, look, we can do this quantum task that you can do with the classical computers. Therefore, we got quantum supremacy. So that's a bit marketing, but it's very often miscommunicated and misunderstood. And one day I woke up, I opened the internet, and I get a message from someone telling me, hey, JP, look, they found how to break RSA with not millions of qubits, but 13,436 qubits. Okay. I read the first page, the second page, the third page, the fourth page. I'm like, what the hell? And someone who was smarter than me on this topic, he found out that somewhere buried in the text, they say, oops, by the way, we need 430 million memory qubits as an implementation detail. So, yeah, don't always trust the scientists because, you know, they have to do their marketing as well. Anyway, I talked about public key cryptography, but public key doesn't encrypt anything most of the time, right? What you encrypt data with, in most cases with phones and with drones as well, you use AES, the Advanced Encryption Standard, which is not public key, which is private key, symmetric key. Symmetric key means you have the same key when you encrypt as when you decrypt. That's why it's symmetric. Can you do something against those symmetric ciphers if you have a quantum computer? The answer is yes, but the answer is no. The answer is yes in theory. In theory, you get a quadratic quantum speedup. It means that if you take the complexity, you put a square root, and the square root result is, in theory, the cost on a quantum computer. However, this is the theoretical asymptotic cost. In practice, it will not directly translate to going from 2 to the 128 to 2 to the 64, where 2 to the 64 is today relatively doable if you have enough GPUs. I also read that it can be applied to machine learning models, but then again, it's most of the time on paper, and I also have the feeling sometimes people want to publish papers and say, oh, we do quantum AI, so it's because it sounds cool. So it's not that scary, to be honest. And even if you find it scary, you have to think about implementing your cipher as a quantum circuit. So I tried to think about it, and I saw some papers that describe the size of the circuit, the depth, the number of layers of gates that you would need. And it's 2 to the 81 in that case. So if you take the diameter of the solar system, if all the gates are as big as one hydrogen atom, and you put them next to each other, then you reach the diameter of the solar system, which is pretty big. So we'll improve on that, but it gives you an idea of how hard it can be. So another paper, we don't care. Anyway, even if you care, we can just use keys of 256 bits, which will give you theoretical 128, and 128-bit security is good. Good enough. OK, now for the last 15 minutes of this talk, I'm going to switch to post-quantum cryptography. You see happy dinosaurs. Well, they don't look really happy, but at least they're alive. So it's called post-quantum. The name is a bit a misnomer because it's not like, OK, we come after quantum and we're even more cool than quantum. No, it's more like post-quantum computer. That is why it's also called quantum safe or quantum resilient, which means that it would not be broken by quantum computers. So it's about public key cryptography that is resilient to quantum algorithms. So obviously, you must not do the same thing as the legacy public key, which is breakable by quantum computers. You remember the two equations I showed, n equal p times q and y equal x power d, yada, yada. So obviously, you should not rely on a hard problem that is breakable by quantum computer. So you can't use factoring, you can't use discrete log. And it's not enough to come up with a new idea like, okay, I make up some weird problem, I have no idea, but it's new, it's not factoring, so it's probably post-quantum. No, you need to build on solid foundations, problems which are known to be quantum hard, so to speak. Okay, why worry about that? Because I don't look, I'm quite relaxed, to be honest. I'm not sweating, oh my God, quantum computers are coming. But it's an insurance. In your systems, maybe you have other fish to fry, other problems to solve, and in most organizations, dealing with the quantum risk should probably not be a priority, but it's like taking an insurance for a low probability, high impact, long-term risk. And if you work in the public sector, you know that it takes a lot of time to get projects, IT projects in the public sector. They fail more often than they succeed, they cost a lot, they really exceed timelines. So if the US wants to upgrade all their federal agencies to post-quantum in 20, 30 years, they need to start now. And that's why they actually started. So people can also read this as, yeah, I'm sure the NSA, they have a quantum computer in their basement, they're hiding things from us. Yeah, they hide things from you, it's their job, that's why it's called a secret agency, man. But I don't believe they do have a quantum computer more powerful than what is public. So they have very good Q&A if you want answers to common questions. It's dates back from 21, but it's still up to date for most of the points. So how does the US NIST, National Institute of Standards and Technology, how do they design new ciphers? Well, they don't. They don't design ciphers. They don't have that much money, especially now with DOU and all that stuff. So they ask other people. They ask cryptographers from, I don't know, Ukraine, Switzerland, France, the UK. They're like, guys, academics, you're a bit bored, right? Okay, you're going to create new ciphers, and you're going to give them to us for free with no IP rights, and then you're going to be famous, or you will feel important. And only if your cipher is standardized. And also NIST, they don't have resources to break ciphers, try and break ciphers. So they do a kind of destruction derby whereby people submit ciphers, but it is in your interest to break other people's ciphers. So it's really cool because anyone can participate. Everything is transparent, public, open source. And at the end, NIST picks what they deem to be the best fit, the best ciphers for their standards. So it started around 2016, like 9 years ago. They had a kind of RFP call for submissions. People submitted stuff. Many were broken. And in 2022, they decided, you will be the standards. You will be the ciphers that everybody's going to use. So in 2022, they selected just one for encryption, but 3 for signatures. Why? They have reasons, and these are good reasons, I believe. So now, they have been turned into official standards, the FIPS line of standards, they have been renamed. So the cipher that was called Kyber, it was a pretty cool name. Now it has a pretty boring name, it's MLChem, a Module Lattice Key Encapsulation Mechanism. And I participated in the Sphinx Plus signature scheme, and it's now called SLH. And stateless something hash. You see, I don't even remember what that means. So, anyway, a few months ago or weeks ago, they chose a new standard called HQC based on codes. And it's public, you can implement it. There are a lot of open source implementations so that you don't have to implement it yourself. So I'm going to give you the intuition, the idea of what we call lattice-based cryptography. The cipher I mentioned before, Kyber, which is really, from my perspective, maybe the best option if you want to upgrade your TLS, even though you will start by combining classical and post-quantum crypto. So Kyber and this signature scheme called dilithium, they work in the following way. That is really an oversimplification to give you the intuition. It doesn't work exactly like that, obviously. But just to show you how simple it actually is, fundamentally. So you have a list or a vector of secret numbers. It's green, it's called S, and you don't know it because it is secret. And then you are the attacker, and the attacker, they will receive two pairs of vectors, pairs of two vectors, sorry, A and B. The first vector, it is just random numbers, uniformly random numbers. So the attacker knows those numbers. And what is B? So B, you combine A and S. So you take the first element of A, you multiply it with the first element of S. So, and you add, with an addition, an error, the red term EI. So you don't get the exact product between the two vectors, you get the approximate product because of the E. If you remove the red stuff, then you exactly get the dot product between the two vectors. So the goal of the attacker is to find S. So without the errors, without the red stuff, it's straightforward to find the secrets. You just divide. You have B equal S times A, so you do S equal B divided by A because you know B and you know A. However, as soon as you introduce E with some special type of probabilistic distribution, then it becomes hard, and really hard, and in fact, NP hard for specifically chosen parameters. So those new post-quantum standards, they rely on the harness of this deceptively simple problem. So you might think that, oh, it might be very slow, this new crypto, it's fancy, it's doing Fourier transform and all that stuff. So in practice, it is not prohibitively slow. The issue in practice, if you talk to hyperscaler engineers, like Cloudflare engineers, they will tell you that the issue tends to be more often the size of the signature or the size of the encrypted text. So here in purple, you have the lattice-based post-quantum crypto. Encaps mean encryption, decaps means decryption. On the white line on top is the standard that we use now in TLS and SSH. So you see we go from 0.072 to, for Kyber, 0.009. So it's in fact faster, and decryption is faster as well. And likewise for signatures, you don't need to look at the number, but it's almost as fast, if not faster. You just have bigger signatures and bigger public keys. So here you see ECDSA public key 64 bytes, but dilithium public key 1,184 bytes. That's much more bytes, right? So the key size might be an issue if you already deal with a lot of data, like Cloudflare does, for example. So let's say you want to use public, post-quantum crypto today. You're like, OK, that was a really cool talk. It's really exciting. I want to go back to my computer and start doing post-quantum crypto. Where do I start? So you go to the internet, and you don't have to write code, because you may, if you use hyperscaler clouds, you may only have to enable the option, I want to use post-quantum crypto. AWS, also Apple, Cloudflare obviously uses it. If you use Cloudflare tunnels, you can do Cloudflare tunnels with post-quantum crypto. If you want to integrate it in your product, there's a lot of open source software, code in C, in Rust, wrappers in all the languages you like, so you don't have to code it yourself. So if you want to learn more about this, I maintain the Awesome Post-Quantum page. There's also the Awesome Post-Quantum Software GitHub page. You can check out the official NIST standards page, and also for the sake of inclusiveness, the standards are not the only NIST standards, but IETF has also been standardizing some post-quantum crypto, different algorithms, of course. And something pretty important, I mean, preaching from my company, but oftentimes you're like, OK, that's good, but I have a company, I use crypto in many places, what should I do? So we wrote a few blog posts when you're a CSO of a company, try to figure out first, OK, let's do an inventory of all the crypto we use. Let's have an inventory of all the keys we have and try to prioritize in terms of risk what is the scariest, where we need to upgrade first, and what are the parts that we don't need to worry about. Because we all have time, budget, boss, and limited energy, so we cannot turn everything to post-quantum crypto. So thank you very much for your attention, and I am here for